Welcome to the final part of the NavMesh Controller series. Last time, we built a simple camera system, addressed rotation, and created our prediction system. Today, we'll use that system to smooth out animations and dive into tips and tricks for tackling animation-related issues. We'll make heavy use of Unity's OnAnimatorIK callback to make everything look just right. Remember, when it comes to making games, it's mostly smoke and mirrors, so let's get started. Before we jump in, let me share a quick backstory. The reason I started building these kinds of systems goes back to a GDC talk called IK-RIG, Procedural Pose Animation. I watched it years ago, back when I was still working on small hobby projects and learning how to code. That talk really inspired me, and it pushed me to dig deeper. Eventually, I came across a bunch of short videos from developers showing prediction systems that could trigger and smooth animations using IK and the predicted data. Seeing that motivated me to experiment and build a few of my own. Now, this series isn't about recreating Ubisoft's IK-RIG. Instead, it's about sharing ideas, different ways you can smooth out and enhance your gameplay. Don't take it as a step-by-step manual of what must be done exactly as I show. For example, in our game EVERGROW, we only use the prediction system to smooth animations slightly. But if you're making something like a survival horror game where realistic character movement matters, and temporarily taking control away from the player isn't a big deal, you could expand the system to fit that need. Or maybe you just want your character to crouch dynamically. That's the beauty of it. You can adapt the idea however it fits your project. Let's start by using the crouch value we calculated in the prediction loop. From that, we'll compute the final crouch value, along with a speed multiplier. We can also move our predicted end position outside of the Unity editor macro, so it actually gets compiled into the build. That way, once we decide to build the project, we'll have it available to affect our crouching. Let's also make sure to multiply our rotation, movement speed targets, and any other relevant values or getters by the speed multiplier, so we don't have to worry about it later. All right, before we dive into crouching, let's fix an issue that could haunt us later if we ignore it now. When the controller moves along the nav mesh and hits a stair, it tends to snap up or down. That might not look too bad at first, but once we smooth everything out and add animation, it'll stand out and look really jarring. To fix this, we first need to unparent the controller model root at startup. Then, we'll let it snap in the X and Z directions, but smooth out the Y direction. This way, movement and gameplay stay responsive while the visuals look much cleaner. As you can see, it already looks a lot better. Now it's time for animation. Let's quickly jump into Mixamo and grab some free animations we can use in our project. Once that's done, let's create our animation controller, along with a function to compute and smooth our animation floats before assigning them to the animator. Let's quickly set up everything on our controller object. We also need to remember to toggle IK pass, so we can use the OnAnimatorIK callback later. After setting up our blend tree, we'll quickly notice some issues, usually coming from the animations we downloaded. The same can happen with custom-made animations. Sometimes, they just don't blend well together. This happens because one animation starts with the left foot while the other starts with the right, which can make them cancel each other out. But don't worry, there's an easy fix. We simply offset one of the animations by 50%. Now, if we test it, we can see that everything is working fine so far. Before we continue, let me show you a simple life hack for dealing with run and walk animation blend trees. We can create a variable to drastically lower our timescale, putting everything into slow motion. Then, we use this slow-mo mode to check for any foot sliding and fine-tune our animations. Now, we need to actually address our foot IK. Let's start by creating some variables to hold our IK targets and instantiate them in the start function. We'll also create a function to raycast down and compute the foot position and rotation using the raycast hit data. Let's also create a couple of variables to hold our foot offset and rotation, and set up a foot IK function that we can run inside the OnAnimatorIK callback. Now, we can use our checkFloor function to compute the foot offsets and assign them to our foot object's position and rotation. We also need to add a bit of the offset to the knee targets so they don't pop around when moving up steep slopes or stairs. Let's also remember to set the foot IK rotation and position weights to 1. It works well, but the feet tend to snap too sharply to the surface. Let's fix that by adding some smoothing. Let's create a simple function to smoothly move our IK targets along the y-axis, while snapping them on the x and z axis, and then use it inside our foot IK function. As you can see, it already looks a lot better. Now, let's address crouching. The first step is to have the character look down and duck his head before actually crouching. Sometimes the crouch amount isn't large enough to justify a full crouch, so just ducking the head can look more natural. To make the character crouch dynamically, we can simply lower the animator's root position by the crouch amount. We can use the speed difference to adjust the crouch when accelerating or decelerating, and we can use the predicted end position to make the controller crouch depending on the slope of the terrain. Let's also use the head hit crouch value that we computed inside our prediction loop. After combining everything, we now have a pretty solid dynamic crouch system. For everything to look right, our character needs to lean in the direction he's accelerating. Let's start by creating a couple of variables to hold our data. Next, we compute our speed delta and smooth out our lean vector. From that, we calculate the final lean up direction and the new forward direction. We can also add some helper gizmos to visualize everything inside the editor. Using our computed direction, we calculate the rotation and assign it to the root. Finally, we need to make sure the foot rotation is adjusted so it doesn't get messed up by the controller leaning. The animations look a lot better now that everything's working. Here's a snippet of the final scriptable object, holding all the relevant animation data along with the default values. And again, we're halfway there. Time to take a break, go make some coffee or tea so you can soak in the rest of the video, or just keep watching. You do you. We can now handle the character rotating his torso slightly toward the target direction before the full rotation. But before we do that, we need to change our rotation action into a func so it can actually return values. After converting our rotation action and all the relevant functions to the correct format, we can quickly test to make sure everything is working properly, just like before. If needed, the movement action could be replaced in the same way, giving us more flexibility down the line. We won't be doing it in this series, but I just wanted to mention it. Once that's all working, we can update our prediction loop to also compute the forward-facing direction. We should also add some gizmos to visualize everything clearly in the editor. Perfect. Finally, we can address our torso rotation issue. Let's start by defining some new variables for rotation speed and angle, and then integrate our torso rotation logic into the lean function. We simply compute the rotation angle and apply it to our forward vector. Right off the bat, we'll notice some issues. The problem lies with the foot targets. By rotating the IK root, we also rotate the foot IK targets around the same axis, which messes up foot placement. We can fix this by making the foot positions relative to the root, rotating them around the root by the same angle we rotated the root, but in the opposite direction, and finally transforming them back into world space before assigning them to the final IK targets. There are still two more issues. First, we need to fix the foot rotation that happens when rotating the root. Second, we currently check for the ground offset and rotation before moving the IK targets, which makes them imprecise. The check floor function should actually be computed after fixing the foot rotation and position. I noticed this while editing the video and didn't have time to fix and re-record everything. Fortunately, it doesn't make much of a difference in this scenario, since the torso rotation angle I used was very small and mostly for minor details. But if you plan to use a larger angle, make sure to move the check floor functionality after this fix. It already looks a lot better. Now, let's address the hand IK and how to make the controller adjust his arms when near walls or other obstacles. First, let's create a couple of public transforms to hold our hand and elbow targets. This will be a simple system, so there's no need to compute dynamic positions. Next, let's quickly set up our hand IK function and assign the targets. We can now conveniently place some spheres in our scene, parented to the controller's IK root, and test everything. To achieve our desired effect, let's create a couple of variables for our hand IK calculations and update the prediction system to check for nearby obstacles. We've already computed the predicted forward vector, which we can use to determine the controller's left and right sides and raycast in those directions. If a raycast hits, we know the controller is approaching a wall. We can then use that information to move his arms toward the IK targets in our animation controller, making it look like the controller is actively avoiding obstacles. As you can see, it's already working properly. Now, we can quickly create a simple walk toggle. It won't be anything fancy, just something to test our hand IK while the controller moves slowly through an obstacle course. With our hand IK working, we've reached the end of this series. I hope I've given you a baseline to create your own system, tailored to your needs. As I've mentioned before, in our project we only use part of the prediction and IK systems to smooth out animation. Maybe you'll end up just using the IK system without even implementing the prediction system, and that's fine. Or maybe you'll just use parts of the prediction system to smooth out movement. Don't pressure yourself into using systems you don't need. Most of the time, less is more. Use whatever fits your game, and tweak or upgrade it to suit your needs. For example, let's say you need your character to be able to do the mighty roly-poly. You could add another movement function and use input to swap it in while the character is rolling, then swap back to the default movement once done. Everything is designed to be flexible, so you can modify or strip it down to exactly what you need. And that's the point of this series, to share ideas and tricks to help make your games better. And as always, all the relevant source code will be available on our Gumroad and GitHub pages. Once I find the time, I'll also make a video for all the Blender artists who just want to use the controller out of the box, showing how to import it into Unity and replace your character model and animations. No coding required. Thanks for watching, and cheers.